this is a supplementary note for the chapter 33, okay, about the electromagnetic wave. Okay, so these slides try to tells you how we can derive all the formulas, or at least some of the formulas at the very beginning of this chapter. Okay, so it's like we try to use the Maxwell equations in differential form, try to use them to derive the wave equations in free space. In free space is important here. Okay, and then so we will get the wave equation, and then by solving the wave equation, okay, the wave equation is actually a very simple partial differential equation. Okay, and by solving this wave equation, we will get the solution for the EM wave. Okay, that is some of the formulas in the beginning of this chapter. Okay, so first I will so I'll let you know what is so-called the Maxwell equation in free space. Okay, so in last chapter for the supplementary note, I've already shown how we can derive the differential form of the Maxwell equation from the integration form. Actually, in the textbook, it's all the way show you the integration form because the integration form is easy to use for hand calculation. For the differential form, it may be more useful for using computer software to do some numerical method solution. Okay, but yeah, here still we can try to use the differential form, yeah, to derive the PDE. Okay, that's the wave equation. So here we will see. Okay, so of course in the last chapter we only know the Maxwell equation only. Okay, we found this in free space. So in free space means okay, Chinese maybe it is called 自由空间。自由空间。那什么是自由空间？ Okay, so here it means that for free space, we have two conditions. One of the condition is rho to be 0, and then the second condition is the J vector is 0. Is 0. Okay. Just in case you forgot what is rho and what is J, so the rho is the charge density. In the space. Okay, so actually it is a function of x, y, z, and also t. Okay, so but usually we consider it doesn't change with time. Yeah. But so this means that there's no charge in the space. Okay, there's no charge in the space, so that no charge will generate the E field. Okay, because back in chapter 22, 23, okay, you know when you have individual charge, okay, or even continuous distribution of charges, then this charge or charges will generate E field in different pattern, depends on how the charge are distributed. And here, okay, so the first condition is that there is no charge in the space. Okay, so no E field generate here. Okay, and then the second condition is J. J is the current density. Okay. No current density means no current. Okay, in chapter 29, when you learn the Ampere's law, you know when you have static current, it generates B field. Or in chapter 32, if there are displacement current charging the capacitor, then there will also be induced E field. Okay, so here we just assume there is no static current, and then in that case, if no charge, which means that no charge varying. Okay, so that means there's no changing E field, so there's no way to generate the induced E field. Okay, so it means that for free space, there is no any source, okay? We can consider this is a source, this is a source, okay? Sources for generating E field and B field. For generating B field and E field, okay? 我们没有任何的源头在这个空间里面去产生任何的这个电场或者磁场。我们假设说它们一开始就是有一个能量已经在那边在作用了所以它只是自由的在传播所以这个是 Maxwell equation in free space. Okay, so it means that for Gauss law on the right side, originally for the integration form, you will be more familiar. So it's something like this. Okay, epsilon naught equals Q enclosed. Okay, so this is the integration form you should be more familiar with. Okay, so in that case, on the right side, it becomes a charge density. And here we just assume that rho to be 0. So on the left side is divergence of E equals 0. And then for Gauss law for magnetism, okay, it doesn't change at all. Yeah. And then for the Faraday's law, doesn't change either. And then for the Ampere's law or Ampere-Maxwell's law, okay, on the left side is curl of B, but on the right side, originally mu J, mu 0 J plus epsilon naught partial E partial T. Okay, originally for the integration form, it should be like integration of a B dot ds equals mu 0 I enclosed plus epsilon naught d phi e dt. Okay, something like this is the integration form for the Ampere-Maxwell's law. Yeah. So this I changed to current density. This electric flux changed to this stuff. Okay, so actually here we have a J equals 0, so this becomes 0. So the right side is simplified to mu naught epsilon naught partial E partial T, like this. Okay, so for free space, it makes the Maxwell equation become easier. Okay, become easier. Two of the terms just vanish. 有两个项消失了，变成零，所以变得比较简单，所以推出来的这个 wave equation 也比较简单之前考试有出过一个题目是假设如果有这个有这两个项的话，推出来的这个wave equation 会长怎么样？就是有考过，不过其实还蛮简单的。Okay, so for the Maxwell equation in free space, the four equations are simplified like this. Okay, and then here we will try to make use of this identity called the curl of curl identity. 就是叫做旋度的这个恒等式curl of curl identity to really derive the wave equation. Okay, so the curl of curl identity, if you just check out the Wikipedia, you can actually find, or maybe you just simply Google curl of curl identity. You also find this. It's like the curl of f and then take a curl again. So it is called curl of curl identity. And on the right side, okay, so we have this one is the divergence. Okay, so this is curl again. And then for this one, this is divergence. And then we take the gradient of it. And then here, okay, this one, maybe you have not seen it before. So, for this one, okay, we have a upside down triangle and then take the square. What does it mean? Actually, in mathematics, you can regard it as the gradient operator dotted with the gradient operator, and its name is called the Laplacian. OK, Laplacian operator， 就是 gradient 跟 gradient 的一个inner product 啊 ，we will get this. OK, this is Laplacian. OK， 那其实要证明这个不难啊，如果在 Cartesian coordinate 的话，你可以带入之前就比如说这个curl of f。curl of f 的话，它会等于这个ijk 啊，然后第一个是 partial x partial y partial z， 然后这个 fx fy fc，OK， 那这个旋度算一次，然后再算一次的话，它会产生好像有6项的哈，因为这里算一次有6项啊，再算一次好像。我忘记了，变6项还是12项，好像我前几天算过一次，反正是可以算出来。那for this side, okay, so for the dot, okay, the divergence is like yeah, so this becomes a scalar field, okay, it's like partial x fx plus partial fy partial y partial fz partial z, okay, so become a scalar field, and then take the gradient again, okay, so take the gradient, okay, we will get 9 terms rather than 3 terms. So if you try to practice it by yourself, okay, so be careful, it comes out to be 9 terms, okay, there will be 9 terms. Okay, and for this one, okay, gradient dot gradient, okay, becomes the second derivative of x plus second derivative of y, and then the second partial derivative of z, okay, something like this, and then acted on the f, okay, so here we will also get 9 terms, okay, 9 terms, because this is a vector, it has a x, y, z dimension, and then yeah, you can also take the derivative, okay, for the partial x, second derivative of x, for the x component, y component, z component, so on and so forth. It also have 9 terms, but altogether it is not 18 terms, okay. Some of them will be cancelled. So if I remember correctly, okay, 6 of the term cancelled, so it turns out to be 12 terms. Okay, so it's like so if you have interest, you can try to practice it by yourself. Okay, so we will try to make anyway. We will try to make use of it. Just believe it is true at the moment. Okay. So yeah, so here we'll try to make use of this curl identity, and then here we will use this one is the Faraday's law, and then this one is the Ampere's law in free space, and then this is the Gauss law in free space. Okay, so we just make use of 3 of the 4 Maxwell equations in free space. So yeah, so here in order to use it, a clear observation is that, okay, we have a curl of E. Okay, so here we try to change F into E, F into E, F into E, so that we have we can make use of it. Okay, and then if we need to make use of it, which means that we try to put it here, which means we need to take curl for the first equation. Okay, so this one. Okay, for this one, okay, for the first one, we try to take curl for the first equation. Okay, it becomes this one, take the curl, okay, become like this, and then this one, take the curl, and then we try to put this curl into this partial derivative. Okay, just believe it is true. Okay, for mathematician, okay, it will ask you whether this one converges, or yeah, it doesn't necessarily to be true, but yeah, for engineering student, we believe it changing the order of differentiation or derivative, the result are still the same. Yeah. So we try to put this one into here so that we will get this, okay? So in that case, here we have this one just like the curl of curl equation on the left side. Okay, so and then here we try to replace f by e. Okay, so on the left side is this one. So we try to change this to the right side. It becomes a gradient of divergence of e minus Laplacian of e. Okay, so we just make use of the curl of curl. This is the curl of curl identity. Okay, and then on the right side, okay, here we have the curl of B. So here, of course, we will make use of the Ampere's law in free space. Okay, so here we try to put equation 2 here. So which means that we try to put this one here. Okay, and then mu naught epsilon are constant, so we can put it outside, and then with a minus sign here. And then here, one partial derivative with respect to time, and then this is the second one. So altogether, we have the second derivative with respect to time for the E field. Okay, so this is the E field goes to here. Okay, so roughly like this. And then we also observe that this one, divergence of E is here. Okay, and then it is 0. So which means we can just put equation 3 here, so this one becomes 0. Okay, so very good. Okay, and then finally we can just multiply the whole thing by -1. Okay, so on the left side we have a Laplacian of E. Okay, Laplacian of E, and then on the right side mu naught epsilon naught, and then second partial derivative of E field. Okay, so this is the first wave equation we can get. First wave equation we can get. Okay, so yeah. So next we can also try to and actually this is for the wave equation. The wave equation for E field. And then of course this is a EM wave. Okay, so you can also imagine we will also get another one for the B field. So we can repeat the procedures, but try to use it slightly different. Okay, here we try to apply this curl identity for the B field. Okay, so in this case, we also try to make use of the Faraday's law and Ampere's law. But here we try to use the Gauss law for magnetism. Okay, so in this case, we try to take the curl for the equation 1. Okay, so we will get the curl of B and then take the curl again. Becomes like this, and then here, take the curl here, and then the curl, put it inside the partial derivative. So it becomes mu naught epsilon naught, partial t, and then curl of E goes to here. Okay, so here we can, of course, make use of curl identity. And then here we try to have F is replaced by B vector. Okay, so that's so that this one is the same as this, and then we can put this one here. So we have a gradient of divergence of B minus Laplacian of B equals this thing. Okay, this thing. Okay, but this one we also observe that this one is the same as this one, so we can put this here. Okay, so we try to put this equation 2 into here. So so on the right side we have one negative sign going here, and then mu naught epsilon naught here, and then we have a partial t. So we have a second derivative with respect to time for the B field. Okay, go to here. And then finally, we have this one. Okay, this one is equation 3. We put this one here, and this divergence of B is 0. Okay, so this term also vanish. And then finally, we also multiply the whole thing by -1, so that on the left side we have Laplacian of B equals mu naught epsilon naught, second partial derivative of with respect to time for the B field. Okay, so this is the wave equation for the B field. Okay, actually this one and this one are the same, except this is E field and then this is B field. Okay, so the only change, only difference are the E field and B field. Okay, so here we have the wave equations, okay, for the E field and for the B field. Okay, actually in previous chapter, I forgot, it's around chapter 16, 17, something like that in the textbook. Okay, it actually have mentioned about the wave equation, but for the mechanical wave equation. Okay, at that time the equation is somehow like this. Okay, the second derivative in the space. Okay, this is the second derivative in the space, and then this is the second derivative in the time, and then the wave equation at that time will be like something like this. Okay, like this, phi and then equals 1 over v square times something like this. Okay, something like this. Okay, so this is the wave equation in a mechanical sense 就是这种什么，就是比如说有一根雪人在那边震荡的那种 wave equation。OK， 那这个项的话是一个1除以 v 平方 ，v 平方是那个speed of the wave. Okay, so comparing this one and this one, we will know. Okay, so here this is not v. Okay, so this will be mu 0 epsilon naught mu naught epsilon naught equals 1 over c square. Okay, for that one v for the speed of the wave in a mechanical sense, but here is the speed of light. Okay, we use c instead of v. So here, first of all, we can get c equals 1 over square root of mu naught epsilon naught. Okay, so this is the speed of light in free space. Okay, so actually we can also use this one to rewrite these two equations like this. Okay, and actually, as I mentioned, the Laplacian operator is something like this. Okay, the second derivative for the xyz. Okay, so this is a general 4-dimensional equation. Okay, because it includes x, y, z dimension and also the time. Okay, 所以这个是一个4维的式子。那我们或者是空间里面是3维的，空间是3维，1维是时间。那我们简单的话，我们就是解一个1维的因为你透过比如说它如果只是沿一个方向去震荡的话，那你就把这个坐标轴旋转到震荡的方向，把 x 轴是垂直震荡的那个方向，那式子就会变得简单。那我们就只需要考虑这一项，其他的就先不管但 generally 如果你有很多个 wave 朝不同的方向的话，那可能你对准一个，其他的对不准，所以最终还是可能需要这个。但是如果我们简单的情况，我们就先考虑一个。所以 so in that case, if we just consider the one-dimensional case, the Laplacian is simplified to the second derivative with respect to x for the E field and also for the B field. And then on the right side is the same. And we also assume that E field, okay, for this case, if I need to write it completely, it will be like the Laplacian of E field in x, y, z component and also the t, okay? And then equals 1 over c squared, and then second derivative of with respect to time, and then for the E vector x, y, z, t, okay? 所以这个电场的话，在空间的每一个点 x, y, z 每一个点都对应一个电场，它还是一个向量。然后它还跟时间有关，所以它是一个四维的，就是有一个四个输入的一个 field 的一个函数这样。那现在的话，如果我们对准一维的话，那我们的话就假设跟 y 跟 z 无关，所以 E 只是跟 x 跟 t 有关啊 ，E 只是类似的 b 也是一样，我就不重复再写一次，只是把 E 换成 b 而已。Okay, so here we try to solve for the wave equation in this one-dimensional space for the free space. 那这个的话其实是，虽然它这个叫做 PDE 啦，就是叫做 partial differential equation， 就是叫做偏微分方程啊。数学系的人听到应该会脚腿软了啊。但是这种是一个最简单的一个形式啊，最简单的解法就可以解。那所以的话，解起来还蛮简单的，那所以这个方法叫做 ，so this method is called a separable of variables， 叫做变量分离法，或者是中文类似的意思，反正就是。它的意思是我假设因为这个 E 是 x 跟 t 的函数那我就假设说 x 的函数跟 t 的函数可以分开，假设是这样这个是一个 assumption， 这个是一个假设你说如果不是这样怎么办？那这个方法就不行。就是这么简单，但是这个方法很简单，所以通常人去解一个偏微分方程的时候，先是这个是很正常的，因为如果行的话，就会很简单找到它的解。万一不行的话，可能要用一些比较复杂很多万倍的方法，就比如说傅立叶级数或者是什么样的，甚至是数值解，那就很困难。那所以这个。因为方法很简单，所以先试无妨。OK， 所以它的最终的用意是，先假设说就是 E 里面的 x 跟 t 可以分离，然后最终我们真的目标是把x 跟 t 的函数也分离，这个是目标。如果能够做到这个事情的话，代表说这个方法 OK。如果不行的话，那这个方法就不 OK，就是这么简单，所以是假设它可以分离，最终真的把它分离先在这个层面把它分离，但是最终的话在方程的层面也把它分离如果做到的话，这个是 OK； 如果做不到的话那这个方法是不行那在这个 wave equation in free space 的话是最简单的情况，所以可以OK, so here we can okay, so here after making this assumption, we can just try to put this one into the wave equation we would like to solve. Okay, so here we will use a blue color to highlight the EX of X, and then use the green color to highlight the ET of T. Okay, so So on the left side, it is a second derivative with respect to x 对于 x 的二次偏导数Okay, so in that case, t is a constant to x. Okay, so we can put this one outside, and then so this one is a only function with respect to x. So we try to change this partial derivative into an ordinary derivative. Okay, 因为本来的话是这整个是又有 x 又有 t 是多边数的，所以我们还是用这个偏微分。但是当这个 t 因为对于 x 来说是常数，所以拿出去之后，这个是纯 x 的函数，所以这个偏微分就不用写偏微分，可以写常微分。那我们就可以写小节 d 而不是写这个 round。OK。 Okay, on the right side it is similar, but here is the second derivative with respect to time. So which means this ex of x is a constant with respect to time, so we can put it outside. So the remaining stuff, okay, second partial derivative of t with respect to et, with respect to time for the et. Okay, so yeah, so this is a pure function of time. Okay, so we try to rewrite this partial derivative into an ordinary derivative. OK， 所以我们做了一些化简有一些可以放出去变成一个常微分。And then we try to separate the x and t. Okay, so here, this term is green. Sorry, this term is blue. This term is blue. This term is green. And then this is a constant, so it doesn't really matter where do we put it. But here we try to divide ex of x and then et of t on both sides. So on the left side, et of t cancels. So becomes this one go to here and then divided by 1 over ex of x. And then on the right side, ex of x cancels. So becomes 1 over c square, and then this term go to here, and then et over t goes to here. Okay, and then finally we successfully separate the function of x and function of time. Okay, so this is a function of x, this is a function of time, right? But they are equal to each other, which means that they are all equal to 0. 因为两个函数，这个是 x 的函数，这个是 t 的函数，它们永远相等，它们永远相等。所以它们一定是等于同一个函数不然它们不会相等比如说你比如说我带 t 等于0进去这里就肯定是会变成一个常数嘛。那所以的话左边就会等于这个常数那无论 x 怎么变的话也是等于那个常数。那当我 t 在变的时候也应该等于那个常数所以是这个道理。Okay, so this is the punchline for the separate of variables method for solving the PDE. Okay, 就是说我们先假设这个函数是可以分离的，那我最终带进去之后，我们还是把这些变数分离之后，我们就可以说它们各自等于一个常数，那这个就会变成一个常微分方程，二阶的常微分方程，那就很好解。Okay, so in that case, to solve this one, we get this first one equals to a constant a, this one equals to the same constant a. So we try to move this one to the right side, move this one to the right side. So becomes second derivative of ex equals a times ex, and then second derivative of et with equals ac squared times et. Okay, so this is the second order constant coefficient, ODE. Okay, so here we assume three cases. The first case is a is larger than 0. A is larger than 0. So yeah, if you still remember to solve this kind of ODE, okay, we would like to change the second derivative into s squared and then equals a times s. Okay, a times 1. Okay, so this is the original function. Change it to 1. Okay, so if a is larger than 0, which means s equals plus or minus square root of a. Okay, so which means ex of x equals exponential to square root of ax, and then also exponential to negative square root of a times x. Okay, but this one is not interested. We do not interested at it because this function will decay. Okay, it doesn't oscillate, so we don't really like this. We don't like this case. Okay, because for the EM wave it must oscillate. It must oscillate to transmit. Or in other sense. Okay, so x when x tends to infinity, okay, this one will tend to infinity, which means the E field also goes to infinity, but you need infinite energy to generate this E field, so it doesn't make sense. So we don't like this kind of solution. Okay, so we just don't like case 1. Okay, so for the case 2, a equals 0. This is a similar case, so which means ex will be a linear function, a plus bx, and then et will be c plus dt. Okay, this is a linear function. Similarly, when x goes to infinity, okay, this e will also go to infinity, but yeah, we need infinite energy to generate this E field, but it doesn't make sense. So for case 2, it is not good either. So for case 3, we have a is smaller than 0. So s squared equals a, but a is negative value. So here we try to let a to be negative k squared. Okay, to be negative k squared. S squared to be negative k squared, so which means s equals plus or minus j times k, j times k, or I times k, or I times k. It just depends on whether square root of 1 equals to I or j. Okay. Yeah, in the textbook in the textbook it doesn't have this derivation, but yeah, sometimes I used to use the j instead of I. Yeah, but here I still use I. Okay, so if you still remember, if we have this kind of complex conjugate roots 这种共二复数的解 Okay, so in that case, of course the real part 实不是零，实不是零。本来的话是说 s 等于 alpha 加 j beta 的话，或者 I beta 的话，它的解的话是ex 会等于exponential to alpha t and then cosine of beta t 加 sin beta t 像应该是有 C1 C2 才对 C2 OK 有 cosine 有 sin 是虚部的，实部是这个 alpha， 但是这里实部是0的话 exponential to 0是1，所以就没有这个项了，剩下的就只有 cosine 跟 sin。 OK， or actually we can just use this kind of we don't try to simplify it at this moment. Okay, so because when you try to get this characteristic polynomial, we try to assume that ex of x equals exponential to s x, something like that. Okay, and then here we get s equals plus or minus jk or ik. Okay, so here we get exponential to ikx or exponential to negative ikx to be the solution for the first one. And for the second one, okay, here we will get s squared equals ac squared, okay, which is a negative k squared c squared. So here for the second one, we have a s equals plus or minus jkc. So in that case, we have et of t to be exponential to jkct, but here we will have omega equals kc. Okay, omega equals kc. Why it is like that? Because we have k is the wave number. If you still remember, is 2 pi over lambda. K is 2 pi over lambda. And then c, okay, so k times c is 2 pi c over lambda. And then if you still remember, c over lambda is f. Okay, so this is 2 pi f, which is omega. So kc is actually omega. So we will get this one to be exponential to I omega t. or exponential to negative I omega t to be the solution of et of t. Okay, so here generally because these two are the solution, so which means we can actually write it as ex of x to be let's say a exponential to ikx plus b. Maybe I don't try to use a, b, c, d because c will be the speed of light. Maybe I use I don't know what to use. PQRST. Let's say s plus t exponential to negative ikx. st, and then et of t will be u exponential to I omega t plus v exponential to negative I omega t. Okay, so it is like the linear combination of these two to be the general solution. Similarly, for et of t, the linear combination of these two to be the general solution. Okay, and then if you still remember at the beginning, we assume that this e of xt to be ex times et. So which means ext to be this one multiplied by this one. And then you can try to cross multiply. Okay, 就是说这个会等于 ex of x 乘以 et of t 这两个乘起来，然后你把它展开成四项的话，它就会有，比如说这个正的 ikx 跟正的 I omega t 跑到这里，跑到第三个，然后正的 ikx 跟负的 I omega t 跑到第一个，然后负的 ikx 跟正的 I omega t 跑到第二个，然后负的 ikx 跟负的 I omega t 跑到最后。Okay, so this is ex of t, but this is a complex function， 就是这个一个复数嘛。因为如果还记得的话 ，exponential to I 一个东西的话，等于 cosine 这个加上 I 乘以 sin of 这个东西嘛。所以它还是一个复数的函数，但是这个电磁波应该是一个实数嘛，因为它是一个实在的空间，然后我们写了一个实数的方程解出来，不可能是复数的嘛，复数的函数嘛，然后我们也假设说，我们只考虑正的方向，正的方向的话，我们就只考虑前面两个，就是说。这里有这个 kx 减 omega t，kx 减 omega t 的话，这个是往正的 x 方向传播的，而这个 kx 加 omega t，kx 加 omega t 的话，这个是会往负的方向传播的。因为你如果记得的话，上一次我们在讲这个 speed of wave 的时候。speed of wave， 对，在这里讲 speed of wave 的时候，因为这里有个减号，移完之后，这个就会是一个正数。但是如果这里是一个加号的话，那这里就会多一个负号，这代表说它往负的 x 方向传播，所以。我们为了简单，我们就先考虑一个方向的我们就先假设说这两个都是0就不管它，所以只剩下这两个。然后最终的话，所以我们只考虑这个就不考虑，所以我们就假设说 c 等于 d 等于0往 x 方向传播。然后再来的话，就是如果 A 跟 B 是一个共2的关系的话，它们是 complex conjugate 的话，这个就会变回来一个实数的函数，只有 cosine 的部分，OK， But in the textbook, it uses sine here, okay, but it doesn't really matter because sine and cosine is just a shift, okay, a phase shift, okay. Actually, you can also add a phase here to make it more general. 所以课本的话，就是 E field 跟 B field 的话，都是用 sine， 然后都没有 phase。那如果你想很 general 的话，那你就加一个 phase 上去。那其实这个 phase 在不同的平移的时候 ，cosine 跟 sin 就是差个90度，甚至是如果你的轴没有移好的话，它可能有一个相位非零的。那最简单的话就是没有相位用个 cosine 或者两个一起用 cosine 或者两个同时用 sin 都无所谓课本的话两个都 sin， 但是这里推出来的话就 cosine 的话比较直接。Okay, so this is for the E field. Okay, for the B field, we can also do some calculation. Okay, actually we have a E of xt to be like this. So we can make use of this Faraday's law and then consider it in one-dimensional. Okay, for one-dimensional, we have a partial E partial x equals negative partial B partial t. Okay, so in that case, partial B partial t equals negative partial E partial x. Okay, we just move this negative sign to the other side. Okay, so we try to take the derivative of the E field, with respect to x. Okay, partial derivative. Okay, so for the partial derivative, okay, cosine becomes negative sine. Okay, so this negative sine and this negative sine becomes a positive, and then becomes a sine of kx minus omega t, and then em goes to here, and then for the chain rule, we also need to take the partial derivative with respect to x for the argument. So here we have this k coming out. Okay, so this is due to the chain rule. Okay, and then this is partial b partial t equals this one. So we try to integrate on both sides. Okay, on the left side it becomes b of xt. And then on the right side, okay, here we have a sine. Take the integration becomes negative cosine. And then here, also due to the chain rule, we need to divide by negative omega. So this negative with that negative become positive here. And then we have a KEM, and then divide by omega here. Okay, so KEM over omega, and then cosine of this stuff. Okay, so this one is actually BM. Okay, which means we have K times EM over omega equals BM, which means EM over BM will be omega over K. And then previously we already derived that K times C is omega, so which means omega over K is C. So we also get this formula. EM over BM is a fixed ratio of C. 这是另外一个式子所以其实我们已经推了4个式子，一个是这个光速33.3在这里，然后这个33.1在这里，然后33.2也在这里，然后33.4也在这里。Okay, so actually these two are the solution to the wave equation in free space in one dimension, plane wave. Okay, so the solution will be like that. Okay, if we need to generalize the solution into three-dimensional, it becomes this become E field of R vector, and then B field of R vector T. Okay, so it becomes three-dimensional in space. And then what we need to change is that the K, the wave number becomes a vector. So it dotted with the with the positional vector. Okay, originally k times x, but here the k vector dotted with r vector. Okay, so as this one. Okay, so this is the general three-dimensional plane wave for the wave equation. OK， 而这个就是传播的方向，这个是传播的方向，这个是传播的方向。而原来一个维度的话 ，x 是传播的方向，传播的方向。那你说这个电场磁场是什么方向？什么方向？那你可以按照这个右手定则来决定，右手定则来决定，因为那个意思是 E field 要跟 x 轴去垂直 ，B field 的正当方向也跟 x 轴垂直，然后 E field 跟 B field 也垂直。再来的话 ，E field 的方向跟 B field 的方向做 cross product， 就是右手定则的话会指向这个 x 的方向。那你说是不是一定是 y 方向 y 轴 z 轴啊？这个是 y 轴 z 轴，也不一定，它可以在 yz 平面上面旋转，只要维持着它们 y 跟 c cross 190度之后指向 x 方向就可以。所以如果我们还知道 E 的方向或者 B 的方向，我们就可以决定另外一个。就是3个方向我们知道2个，我们就可以决定第3个。Okay, so yeah, so this is originally an animation, yeah, but yeah, the JavaScript does not support anymore, so we cannot see this one. Okay, finally, I would like to talk about the energy density of the EM wave. Okay, so in the equation we have EM, BM to be the magnitude or the amplitude of the oscillation. Okay, we can also use the root mean square value by dividing EM, BM by square root of 2. Okay, before we also have learned that the energy density stored in the E field, the energy stored in the B field are 1/2 of epsilon naught E squared and 1/2 mu naught B squared. Okay, in chapter 26 or 5, chapter 25 and chapter 30, yeah, around that when we introduce the capacitor and inductor. Okay, so these are the energy density stored in the E field and B field. Okay, here what we want to show is that in the EM wave, the energy density of the E field and B field are actually the same. So here, UE is 1/2 of epsilon naught E squared. And then previously we have E equals C times B because E over B is a fixed ratio of C. So E equals C times B. Okay, so at this stage we don't need to care about whether it is EM or ERMS. Just imagine they are the same thing, it's okay. Okay, so here we just distribute this square to C square and B square to be like this. And then we here make use of a C square. C equals 1/2 square root of mu naught epsilon naught. Okay, just plug in the speed of light here. So C square will be 1/2 mu naught epsilon naught. Okay, so the green terms goes to this green term, and then we can cancel this epsilon naught and this epsilon naught. So it becomes B square over 1/2 mu naught, 2 mu naught. Okay, so this is the energy density stored in the B field. So inside the E field, inside the EM wave, as much as we have this green identity and also this blue identity, okay, we can show that the energy density stored in the E field and B field in the EM wave are the same. So the total energy density will be U equals UE plus UB So UE and UB are the same, so it is simply as 2 times the UE, so which is epsilon naught E squared. And then if you still remember, in this chapter we have introduced the pointing vector. Okay, so the pointing vector is 是蛮重要的啊，常常会考的啊。它的方向就是这个传播的方向，就比如说这个是 kx 减 omega t， 那这个 pointing vector 的方向是 x 啊 ，pointing vector 的方向是 x， 而它的大小，这个 pointing vector 的大小是什么？是 energy， 它的能量在单位面积底下，在单位时间里所传播的量。Okay, so it is like, so this is the magnitude of the pointing vector. The magnitude of the pointing vector will be like the c times this is the speed of light times this one, the energy per volume. Okay, why it is like that? Because this one, you can consider it is like, so the energy per volume. Okay, so we try to make it like energy per volume. So here we have a volume over the time and then over the area. 啊，所以就是说，这里比如说有一个空间，我们考虑这个空间，然后这个空间里面的能量在传播，那这个 energy per volume 就是这个东西嘛，就是 epsilon naught E square 嘛，所以就跑到这里来。那剩下这个为什么是速度？因为这个是面积嘛，就是这个截面面积。截面面积的话是这个，然后如果是体积，这个的体积除以这个的表面积的话，就代表说它移动了多少长度，就是这一块的能量移动了多少距离，那移动了多少距离除以时间，那就是这个速度嘛，所以。So this one volume divided by area is the length, and the length over time is the speed of light. Okay, so it becomes c times epsilon naught E squared. And then finally, we can do some simple calculation. So first, E. We can change one of the E into C times B. Okay, so it becomes E times C times B, and then times epsilon naught C. Okay, epsilon naught C goes to here, and then E becomes C times B. So it becomes E times B, and then we have altogether C squared, and then times epsilon naught. And then here we also use c squared to be 1 over mu naught epsilon naught. So EB times epsilon naught over mu naught epsilon naught. Okay, and then finally epsilon and epsilon cancel. It becomes EB times mu naught. Okay, so what is this? Okay, if you still remember in the textbook, the pointing vector is written as E cross B. 1 over mu naught. Okay, so this is the magnitude EB mu naught. Because E and B are always perpendicular to each other, so E cross B, the magnitude will be nothing but E times B. Okay, so EB mu naught is actually the magnitude of this vector, and then in this formula, it also indicates the direction. Okay, so this is the E cross B will be the direction of the pointing vector, which is the direction of the wave propagation.